The Saturn V stands primed, 160 million horses and 3 astronauts raring to go. The plan? Exploding bolts and anchors will release the rocket from these massive steel gantries and support structures. When the engines ignite, these attachments should all simultaneously detach and swing away before their momentum, size, and weight bounce them back against the rising rocket. Enter Paul Taylor. His company, Taylor Devices, had for years been making liquid spring motion dampers used by the Navy. These high-tech shock absorbers would prove ideal to control the heavy, unwieldy cables and swing arms of the giant Saturn V. NASA hired Taylor to design damping systems for Apollo launch operations and later shuttle missions too. In the 1990s, Taylor Devices applied the same fluidics technology to protect buildings during an earthquake. These massive seismic shock absorbers are used in steel, concrete, and bridge structures worldwide. Not a single structure protected with Taylor's seismic dampers has ever failed during a quake. Who'd have thought that going to the moon would help protect us during an earthquake? 50 years on, we are all heirs to Apollo, beneficiaries of all this technology it took to get 12 men to the moon and back. Who knows where we'll go and what we'll find out in the next 50 years? You need powerful radios to communicate with satellites, rovers, and astronauts, and NASA has been exploring, pushing the limits of space communications for decades. In 1993, scientists and engineers at Lewis, now Glenn Research Center, and Lockheed Martin helped launch and orbit the Advanced Communications Technology Satellite, ACS. It was the first all-digital communications satellite. Programmable radio spot beams operated in the uncrowded high-capacity Ka band. ACS provided an innovative technology testbed. So innovative, it was inducted into the Space Technology Hall of Fame in 1997. Today, some members of that same pioneering communications team are here again, 2019 inductees into the Space Technology Hall of Fame. Space radios are unique. Each piece of hardware, radiation hardened and validated for the extremes of spaceflight. And once on orbit, spare parts are hard to come by. Software, however, can update systems easily. The ACS platform showed how software could operate and update on-orbit hardware, allowing radios to become more flexible and adaptable. Fast forward to 2012. Seasoned scientists, researchers, and engineers from NASA Glenn and Harris Corporation worked together to develop the first Ka-band software-defined radio qualified for space applications. Sometimes called a computer with antennas, software radios were used by the military, but earthbound systems were too heavy and cumbersome for spaceflight. The NASA Glenn Space Communication Team persevered. After 5 years of efforts, the newly designed SDR is put into service aboard the ISS on the SCAN testbed. The NASA Harris Ka-band radio has proven successful in space, and Harris developed a commercial product called the APSTAR Software-Defined Radio System, designed to run multiple applications, much as smartphones do today. 75 second-generation Iridium NEXT satellites are now equipped with APSTAR SDRs. More than 250 of these radio configurations are in orbit today. APSTAR radios will enable partner Aireon to provide a real-time space-based monitoring system to continuously link aircraft worldwide. The company exactEarth has developed a similar maritime concept, providing ship tracking services. Telemedicine, education, and other third-party users are developing software applications for the system already in place. Water, food, sanitation, sleep, cabin fever. Long-duration spaceflight is challenging, and physical exercise is crucial for health. Astronauts experimented with a variety of exercise devices. The goal? Prevent debilitating muscle and bone loss. In 1996, for 188 days, astronaut Shannon Lucid diligently used Mir's stationary bike and treadmill as much as possible. she still experienced significant loss upon her return to Earth. For upcoming ISS missions, NASA had to come up with a better solution. Dr. Roger Billica at NASA's Johnson Space Center suggested that resistive exercise equipment might be the best solution. Inventor Paul Francis made a submission. His idea was to use spiral springs wound into discs called flex packs. The concept, later branded Spiroflex, provided a linear resistance that simulated working with free weights. Paul's proposal was selected, and with NASA funding, he oversaw the design and production of the new device dubbed IRED, or the Interim Resistive Exercise Device. The system was completed in time to launch with ISS Expedition 1 in 2000. Spiroflex technology was also used in a commercial Schwinn product, and enhancements made were incorporated back into the IRED on ISS with help from NASA physiologist Mike Rapley. An updated version known as ARED now flies inside ISS. Paul Francis and his company, Spiroflex, own the technology patents. Nautilus Incorporated purchased Schwinn, and in 2005 introduced the Nautilus Bowflex Revolution line of exercise equipment. It uses the Spiroflex technology and is sold today. Paul Francis has also started a new company, Oyo Fitness, with a new line of equipment utilizing the Spiroflex technology. It's another example of how learning to live well in space has been a boon to living well on Earth. Today, we induct into the Space Technology Hall of Fame Ka-band software-defined radio, APSTAR. Interim Resistive Exercise Device, Spiroflex. The Space Foundation is proud to honor and acknowledge the scientists, researchers, engineers, and others whose imagination and inspiration helped create the products and services originally designed for use in space that today improve the quality of all our lives here on Earth.